So yesterday we looked at graphing rational functions. Today we're going to look at solving equations that are rational functions. So a couple of things we have to be careful about. When you have a rational function, that means you've got a polynomial usually in the numerator and the denominator. And we always have to be careful that the denominator is never what number? Yeah, we'll make sure the denominator is never 0. And if you find an answer to a rational equation that would cause the denominator to be 0, then it's not an answer. And we have to say that. Okay? So we'll look for things like that too. We're going to start out by solving some equations algebraically. We might look at some graphically as well. And the first problem we're going to look at is a word problem. And it's going to be a distance, rate, time problem. So we do need to remember that formula, which is distance equals rate times time. So d is your distance, r is the rate or the speed of the object or the thing traveling, and t is the amount of time that it's been traveling for. Okay, so d equals rt. That would be a formula you'd be expected to know now that I've shown it to you for the test if a problem comes up with distance, rate, and time. All right, so this problem says that Sue drove 30 miles to a train station. So took her car, 30 miles, drove to the train station, and then from there, got on the train and completed the rest of her trip. In all, she traveled a total of 120 miles. And we know that the average rate of the train is 20 miles per hour faster than the average rate of the car. That's all the information they give us. So they want us to figure out the time that it's going to take for her to complete the trip as a function of x, which is going to represent the speed of the car. So in other words, when we're done, we're going to have a formula that if you tell me the speed of the car, I can plug that into the formula, and it'll automatically calculate how long this trip is going to take. So the first thing is they are asking about time. So we should probably rework that equation they gave us so that it is in terms of time. So what would be the distance equals rate times time formula if you solve it for t? Yep.
Distance divided by rate equals time.
Distance divided by rate equals time. Yep, perfect. So let's write that down. Distance divided by rate equals time. Now, how many modes of transportation is Sue taking in this trip? Okay. 2. And we want to find the total time for her trip. So what would we have to do with the time she spends using each mode of transportation to find the total time for the whole trip? Yeah. Yeah, we're going to add them together. So the big idea is the total time to complete the trip. It's going to be the time that we're in the car plus the time that we're on the train. Okay, so let's start with the time that is spent in the car. So we know time is distance divided by rate. So we need the distance in the car, and we need to divide by the rate of the car, and that will be the time in the car. What's the distance that we travel by car? Yep, 30 miles. And what is the speed of the car? Yep. X. You take the distance and you divide by the speed. That's the time that she'll spend in the car. 30 divided by X. Okay, now the train. What's the distance that she travels by train? Yeah.
90 miles.
90 miles. We didn't get that information, but we know it was a total of 120, and she did 30 of it by car. So the other 90 was by train. So that's the distance, and now I need the speed of the train. What's the speed of the train, or how is the speed going to be represented? Yep.
X plus 20.
X plus 20. That is a formula that represents the time it's going to take to complete this trip. Now, we might want to manipulate that. We're probably going to want to put that together with a common denominator. But for now, that is the formula that they asked for. Any questions on how we got that formula? Okay, so now we'll do some calculations with it. So they want us to find some asymptotes, the roots, the EBM, and a sketch on the calculator. Well, for some of that, we do want this combined together. In order to add two fractions up, you need to make sure you have what? Yep.
Common denominator.
Common denominator. And what would my common denominator be in this case? Yep.
X.
That will be part of it, but we're going to need, it's going to have to be a little bit more than just X. Yep.
X squared plus 20x.
Yeah, it's the product of the two denominators that you have. I'm going to leave it factored just because that's going to make finding the roots of the denominator easier when they ask for asymptotes. So it's going to be xx plus 20. What would you have to multiply the fraction on the left by in the top and the bottom to make it have the common denominator? Yep.
X plus 20.
X plus 20. And what would you have to multiply the fraction on the right by to make that have the common denominator? Yep.
X.
Just X. Okay, so we already got the common denominator, xx plus 20 written. My numerator is going to be 30x plus 90x. That's going to give you 120x plus 600. Because remember, that has to be distributed and then combined with 90x. Okay, so now we at least have it all together, so that might help us to do some things. Let's do the EBM first. That's usually easy one. Okay. What's the highest degree term in the top? Rush?
120x.
120x. And what's the highest degree term in the bottom? Yep.
X squared.
X squared. Yep. You got to think of how it would be if you did that out. And that's going to leave me with an EBM of what? Yeah. 120 over X. Okay, so we got the EBM. Find the asymptotes, right? Well, since the degree in the bottom is bigger than the top, we're not going to get anything curved for an asymptote, but we are going to get what kind of asymptote when the degree in the bottom is always bigger. Yep. We're going to get a horizontal. Yep. So horizontal asymptote, or any asymptote, has to be written as an equation. Don't write it as a single number. EBM can be a term. That's fine. But asymptotes need to be equations. So horizontal, y equals. And what happens to the EBM as x approaches infinity, what does the EEM approach? So
0.
this approaches 0. Yep. So there's your horizontal. Vertical. What are we looking for when we're trying to find the vertical asymptotes? Yep.
The roots of the denominator.
Yep, roots of the denominator, as long as we don't have any common factors, but the only thing you could factor out at the top, I mean, I guess you could factor out like a 120 from each of them, but it's not going to give you one of the factors at the bottom. So you will have 2 vertical asymptotes. What will my 2 vertical asymptotes be in this case? Yep.
0 and negative 20.
So those are the roots of the denominator, but what would the asymptotes be?
X equals 0, x
Yep.
equals negative 20.
X equals 0, x equals negative 20. Okay, I think we're good with asymptotes now. So we've got all those. We've got the EEM. They want us to find the roots. Okay, the roots, or the zeros, those are the x-intercepts. How do you find an x-intercept in an equation? You have to plug in something for something. How do you find x-intercepts? Yep.
Plug in 0 for 1.
Plug in 0 for y. Yes. So when we find the x-intercept, remember this is your y. That's your independent, the time. I'm sorry, that's your dependent, okay, the time. So set this equation equal to 0 and solve. Well, the only way that that's ever going to be 0 is if the top is 0. So just figure out when the top is 0. So 120x plus 600. If you subtract the 600 to the other side and divide by 120, you will get negative 5. Yes? Okay, so we got the x-intercept, we got that's the 0, we got the EDF, we got the asymptotes, that's it. We got everything we need. Okay, let's do the sketch. Okay, when I do the sketch, I'm going to use the version that we combined together because it's just easier for me to type that in. So 120x plus 600. And I am going to distribute the bottom and make it x squared plus 20x. If you want to use one of the original versions, you can. You're just going to have to do more parentheses. Now, they are specifically asking for a complete graph. That is not in reference to the word problem. A complete graph means the whole thing. All right. So let's start with Zoom 6. See how that looks. Okay, so what do we think? Does that look like a complete graph? No, I can't really tell well what's going on. And I have a vertical asymptote at negative 20. I'm not even seeing that in the picture. So no, that's, if you're looking for a complete graph, that's not it. I would set your window to go to maybe negative 40. Let's start by adjusting that. Okay, so there's a part of the graph we weren't even seeing before. So it's definitely in 3 pieces. Let's go out more, okay, on everything. So what I'm going to do is I'm going to do zoom 3, and I'm going to hit enter, and that's just going to zoom out everywhere. So I got a lower left piece, I got a middle piece, and I got a right piece. That's a good picture. I can see everything now. Okay, so for a window, since I did zoom out, it's probably going to use, sometimes it uses funny numbers. No, it didn't use any decimals. Those are the values that I used. Okay, definitely not the only values. All right, any questions on that? Now, if we were looking at this in the context of the word problem, what should my x min be? Rush? 0, right? Because x was the speed of the car, and a negative speed wouldn't make sense. Right? So if you're looking at this in the context of that, x min should be 0. And what should y min be? Think about what y is. What is y? It represents what in this problem? Yeah.
Be 0 because it's time.
0 because it's time, right? So really, if you were doing this in the word problem, the only part of that graph you should be looking at is the part in quadrant 1. The other two parts are there algebraically, but they don't make sense in this word problem. Okay. So now it says Sue has 2 hours to complete the trip. Find the speed she must travel by car algebraically and graphically. We're gonna do more algebraically. So let's do this one graphically, and we'll do algebraically later. Okay, so if I'm going to do it graphically, first thing I should do is set my window so that I am only looking at quadrant 1. So that graph represents the time it takes Sue to complete the trip. Can anyone give me a sentence that kind of explains what that graph means? Taking into account the direction it's going and the way it's curving and what's going on here. Yeah.
As x or the speed increases, the amount of time the trip takes decreases.
Yep. As the speed of the car increases, the amount of time it takes to complete the trip decreases. We can say one more thing in relation to it decreasing. What's one more thing we know about the time of this trip? Yep.
It's not going to be 0.
It can never be 0, right? No matter what, the time is always going to have some positive value, regardless of the speed of the car. Okay? Because we have a horizontal asymptote at 0, practically that just makes sense. You can't complete a trip in 0 amount of time. All right, so it says Sue has 2 hours to complete the trip. Find the speed she must travel by car, and we're doing it graphically. Right? So what would I have to do to this graph to find the amount of time it's going to take her to complete the trip, or to find the speed if she completes the trip in 2 hours? How would I use this graph to do that? So remember, that's a graph of the time it takes to complete the trip. So we just have to, something we've done before. Yeah?
Put a line at 2 hours and see where it goes.
Yeah, let's put a line at 2 hours. Okay, that's going to look pretty low on the graph because I'm going all the way up to 40 on the y-max. So if we adjust this to only go up to 10 hours for the maximum trip time, that line at 2 is not going to look like it's right on the axis now. It'll look like it's a little above it. Okay, so I've got a line at 2 hours. And what would I do now? Yeah. Yeah, see where it intersects. So second calc, intersect. Second calc, option 5. Okay, so I found where they intersected. What did I just figure out? What is that telling me? Oh, Jane, what's that telling me?
X is the speed.
Can you be a little more specific?
speed she's at when she's gets there 2 hours?
Okay, I agree, it is a speed, but I need more. I need more information about that.
In miles per hour.
Yes, I believe it was in miles per hour. That's also true. Still something else I need, yeah?
If she wants to make it, make the trip 2 hours long, she must go 46.5 miles per hour.
When you say she must go, can you clarify that?
When driving, if she were to drive by car, she must go 46.5 miles per hour to make the trip
Yes.
2 hours.
That is the speed she drives in the car. It is not the speed of the train. So we have to make sure we know what they're asking for. They specifically asked for the speed of the car, and that is what we have. So, okay, so Sue must travel. Does it say exactly 2 hours? Okay, yeah, so it says exactly 2 hours. It doesn't say she has to complete it in 2 hours or less. That would be a little different answer. But Sue must travel 46.46 miles per hour by car to complete the trip in 2 hours. What would be the speed of the train then? They didn't ask for that, but they could. Yep.
It'd be 66.46.
Right. The average speed of the train was 20 faster than the car, so it would be 66.46. Yep. All right. So any questions on that? So graphically, it's pretty straightforward. You just graph it, find where it crosses. Now, if this wasn't in reference to the word problem, then I could zoom back out, and we know that it's going to cross it in the negatives as well. Okay, so there is an answer in the negatives, it just doesn't make sense in the word problem. So we didn't actually do this, so I'm going to reword it, but we're going to do this next. So I'm going to say, when solving algebraically, if you multiply both sides so when solving algebraically, if you multiply both sides of an expression by a variable, I already had the word variable. This may result in an equation not equivalent to the original. Yeah, so that's fine now. So when we're going to solve algebraically, if you multiply both sides by something that has a variable, that can mess up the original problem, and it can create answers to the question that should not be there. Okay? Those answers that you created by multiplying both sides by a variable are what we call extraneous solutions. They're solutions that you created because of the way you solved it, but they are not solutions to the original problem. So the way we avoid that is we have to check our answer. Generally, what will happen with an extraneous answer is when you try to plug it back in, it causes you to divide by 0. All right, so let's look at this one. Just a really simple equation. And I'm going to show you how you can multiply both sides by the same thing and introduce an answer that's not supposed to be there. Okay. X minus 1 equals 0. What's the answer to that equation? Yeah, 1. Okay, so just keep that in mind. X equals 1. Does anybody think there's another answer for x minus 1 equals 0? Okay, so let's try to solve that, but let's say we did it by multiplying both sides by a variable. So if we multiply both sides by a variable, like let's multiply the left side by x and the right side by x. Okay, so I distributed it on the left and I multiplied it on the right. So the left side is really x times x minus 1 equals 0 if you had it factored up. When you have two things multiplied together equal to 0, you just have to find what makes each one of them 0. First, does anybody think I made any mistakes multiplying both sides by x? Okay, so everyone agrees I did that right? What would you plug in here to make that factor 0? Yep, you'd plug in 1. What would you plug in here to make that factor 0? Yep, you'd plug in 0. So the two solutions to this equation are 1 and 0. Well, if you go back to the original problem, 1 works. We all agreed that was the answer. Does 0 work if you plug it in right there? No. So you created an extra answer that shouldn't be there by multiplying both sides by a variable. That's how that can happen. Now, in this equation, you might think, well, yeah, I would never multiply both sides by x. Right, we wouldn't. But in this one, you're going to have to multiply both sides by something with a variable. There's no way around it. And the reason we're going to be multiplying by a variable is because we are trying to eliminate the fractions. We're going to try to turn this into a problem that does not have any fractions in it. And the way you do it is you multiply by the LCD, okay, least common denominator. Okay, here's the same concept with just numbers. So you had x over 3 plus 2x over 4 equals 5x over 12. Let's just say like plus 2. It'd be a lot easier to solve that equation if there weren't all those fractions. So there is a number that I can multiply everything by that would cancel all my fractions out. What could I multiply everything by there that would cancel all my denominators? Yep.
The least common denominator is 12, so you can do 3 times 4, 4 times 3. For the
So you'd multiply everything by what number?
oh, I guess yeah. Never mind.
So we're looking for something we can multiply each term by. It has to be the same number in each term. It's going to cancel all my denominators. Well, Gregory, what do you think?
I was thinking -2, but I want to look for the x over 3.
Yeah, if we multiply everything by -2, that's not going to get rid of any of my denominators. I'm still going to have denominators there. Yep.
Would it be 12?
12. So I want to multiply everything by, think of it as 3 times 4. So 3 times 4, 3 times 4, 3 times 4. What's going to cancel out in the first fraction when I do that? Travis?
Denominator of 3.
Yeah, the 3, and that's going to cancel with the 3 that I'm multiplying by. Yeah, so the 3's are going to cancel. What about in the second fraction? What's going to cancel out there? The 4's. And how about somebody else in the last fraction? What cancels there? Yep.
12 and the 3 times 4.
Right, the 12 and the 3 times 4. Now you've got a much easier equation to work with. You multiplied everything by 12, so you didn't do anything wrong, right? We got 4x plus 6x equals 5x plus 2. And now you can finish solving it from there. Right, that's much, much easier to solve now that we got rid of the fractions. And in general, a lot of the problems that we do, this number is going to be the product of these two. If it wasn't, then it would just complicate what you have to multiply by a little bit. Like if this number was a 13, well, then multiplying by 3 times 4 would work. I would have to multiply everything by 3 times 4 times 13, okay, which I could do. And there might be a smaller number you can multiply by. But multiplying everything by 3, 4, 13 would at least get rid of all the fractions, if it was a 13. Okay. So now, let's try the same approach on this one. Okay, we already did it graphically earlier. Graphically, we can do one again, but there's different ways you can do it. I would just put all of this in y1, and I would put this in y2, and then we'd be looking for what? Yep.
The points where they intersect.
Right, we'd just be looking for the intersection points. It's exactly what we just did in the last problem graphically. We had a y1 and a y2, and we looked where they cross. All right, so let's do it algebraically. First thing we have to decide is what are we going to multiply everything by? Okay. Let's factor the right-hand side first, because if it is the product of the two on the left, that's going to make it a little bit easier. Okay. How does that denominator factor? Yeah.
X minus 1, X minus 3.
It does factor as x minus 1, x minus 3. If it didn't, then I would look at what it factored as, and I would multiply everything by this, this, that, and that. But since those two are repeats of the first two, I don't need to do that. That would be like multiplying everything here by 3 times 4 times 12. It would work, but it's unnecessary to do 3 times 4 times 12, because this was the product of the other two denominators. All right, so what are we going to multiply everything by in this one? Each term is going to get multiplied by
X minus 1 times X minus 3.
x minus 1 times x minus 3. And don't do that out, because things are going to cancel. If you multiply it out, it's not going to be easy to see what cancels. Okay, so do it there. Do it over there. And one more time over here. What can I cancel out in the first fraction? Yeah.
X minus 1.
Right, x minus 1 is gone. What about the second fraction? Yeah, where is it? X minus 3. And what about on the right-hand side? What's going to cancel there? Yep. The whole bottom, because that is x minus 1, x minus 3. So now if you've done this right, when you're done, you're not going to have any denominators. So distribute that out. So that's 2x squared minus 6x. Be careful when you do the next one. This is what you are distributing. If that was a negative, it would go with that number to be distributed. But in this case, it's not. It's just a positive 1. So distributing positive 1 doesn't change it. So it's x minus 1 equals 2. All right. What kind of equation do we have there now? Yeah. Yeah, we have a quadratic. So factor it, complete the square, use quadratic formula, whatever way you want to solve the quadratic. Okay. with factoring and quadratic formula, we've got to make sure we get it equal to what first?
0.
Yep, get it equal to 0. So let's put everything on the left. And if you combine like terms and get that equal to 0, what would you have on the left side?
2x squared minus 5x minus 3.
Yeah, 2x squared, combine your like terms. Now we can try to factor it. If it works, great. If not, we'll use quadratic formula. So we would do 2x and x. We're going to need a plus and a minus. Those might have to be switched. We'll see. And we're going to need 3 and a 1. Let's check it. 2x squared. That gives you negative 6x plus 1 is negative 5. And 1 times negative 3 is negative 3. Perfect. So it factors. And we get 2 answers. What would be your 2 values for x that make that true? Yep.
Negative 1/2.
Negative 1/2 and 3. Now, you're not done, because one of 3 things could happen. Either both these answers work, one could work and one doesn't, or they both don't work. All right, so we have to check by plugging them back in that we don't get any extraneous solutions. Let's start by checking the 3. Can you plug 3 back into the original problem? And get a numerical answer? What happens if you plug in 3? Yeah?
You divide by 0.
Divide by 0. That means 3 is extraneous. It doesn't mean I won't ask you for it. I might say, give me all the answers and then label anything that needs to be extraneous as extraneous. So you might still have to find it, but you do have to tell me that it is extraneous. The negative 1/2 will be fine. Okay. Generally, extraneous just means it's going to cause you to divide by 0. If you check that, you'll be good. The only way the negative 1/2 would be the wrong answer is if you made a mistake. Okay. You did your factoring wrong, or you did your quadratic formula wrong, something like that. But other than that, those 2 answers are what you would get when you solve this. And we mark the 3 as extraneous. Okay. Any questions on that? All right, so in this one, we had something on the other side, and we multiplied, and then we eventually brought it over to the left. Well, they've already brought everything over to the same side in this one. So it's actually one step ahead of the other problem. Okay, so we've got x minus 3 over x plus 3 divided by x plus 2 plus 6 over x squared plus 2x. What's the first thing we want to do here? Yep.
Factor.
Yep, you always want to factor that term that's more complicated and see if it's the product of the other 2. If it's not, things are going to get a little more complicated. As long as it is, the multiplication is going to be a little easier. Okay. How does x squared plus 2x factor? Yep, Marcel?
X times x plus 2.
It does factor as xx plus 2. So that means we're going to multiply all 3 of these. Well, actually, all 4, but the right side isn't going to change because it's a 0. What are we going to multiply all 4 of those by? Yeah.
X times x plus 2.
X times x plus 2. And, I mean, on this side, again, it's still 0. Okay, now cancel what you can first. Lenz, what's going to cancel in the first fraction?
X.
X. That's good. Dario, what's going to cancel in the second fraction?
X plus 2.
X plus 2. Declan, how about the third fraction?
The whole denominator.
Whole denominator. And now we do what we have left. So the first one, that's a distributive. So you're going to end up with x squared plus 2x minus 3x plus 2x minus 3x is negative x. And negative 3 times 2 gives you negative 6. Now remember, in the next part, what you would be distributing is positive 3. That gets distributed to whatever is left here. So don't forget about that sign going with that number. But it's just positive 3 times x. So plus 3x. Excuse me. And then plus 6 because the entire denominator is gone. And because they moved everything to the left, it's already equal to 0 for you. We just finish it the way we want to finish it, your quadratic. Ideally factoring if you can. Okay, so combine everything together. You're going to get x squared plus 2x. Negative 6 and 6 cancel. And how does that factor? X squared plus 2x. Yeah.
You can factor out x.
Yep. And how would you write that?
X parentheses x plus 2.
Plus 2. So what are your two values of x that you could plug in there and make that equation true? Yep.
0 and negative 2.
0 and negative 2. Okay. And what do we do now that we have both those answers? Yeah.
Check them.
Check them. What's going to happen when we check them?
You divide by 0 on both of them.
Both of them cause you to divide by 0. Because the problem you're solving here is exactly what that factored into there. So 0 and negative 2 are both extraneous. Sometimes the symbol you might see for that, I think that's it's one of the times we don't use a Greek letter in math. I think that's a Norwegian letter. I don't remember the name of it. But the symbol means empty set. Empty set means that there are no numbers that would make this problem true. Or the set of numbers that make it true is empty. There are none. Okay. Any question on that? So the only case we didn't look at is when both answers worked. So this is both answers don't. This was one answer does, one answer doesn't, but you could get both that do work. And quadratic equations come up a lot when you're doing these ones. All right, so now getting into the last thing we're going to look at. They've reworded the problem a little bit to say, at what possible rate would Sue travel if she wants to make sure she completes the trip in less than 2.5 hours? What's different about this question than the first question we asked about this traveling problem? Yep. So the context of the problem is still the same. She's still traveling 120 total miles. The average rate of the train is 20 faster than the car. So all of that stuff is going to be the same. But it's a different kind of question, and it's going to require us to write our answer in a different way. Yeah.
It's asking us to see what the answer would be if she traveled less than.
It's a less than. Okay, this is getting into inequalities. Okay? So when we're doing an inequality, the speed isn't going to be an exact answer for the car. The speed is going to be an inequality. It could be greater than a certain speed, less than, greater than or equal to, or less than or equal to. So we still have the graph. We just have to change 2 to 2.5. So all this is going to be the same. We're still going to find where they intersect. So second calc intersect. so I've got all the information I need. How do I write my answer? She wants to complete the trip in less than 2.5 hours. So tell me how fast she needs to be going in the car to make that happen. Yeah?
X is greater than or equal to 34.88.
Not quite. Yeah.
X is greater than 0, but less than 34.88.
No, it can't. So I do agree the speed has to be greater than 0, but if she's traveling less than 34.88, she's not going to make the trip in 2.5 hours. She'll be going too slow. So we're a little bit closer with the first answer. There's just something technical about it. Yeah.
The speed of the car must be at least 34.88 miles per hour. Well, greater than 34.88 miles per hour.
Okay, so at least 34.88 or greater than 34.88? There is a difference.
It would be greater than, because at least would include equal to.
Right, we don't want to have equal to, because it doesn't say she can complete the trip in 2.5 hours or less. It says it has to be under 2.5 hours. This is the speed if she wanted to get the trip in exactly 2.5 hours. So she has to be going faster than that speed. So the speed of the car must be greater than 34.88. Right, so you do have to just pay attention to the wording. Is it in 2.5 hours or less than 2.5 hours, things like that. Okay, she's got to be going faster than 34.88, and that'll put her in that zone, kind of, which is under the 2.5 hour mark. All right, so rational inequalities. When we're solving rational inequalities, remember we always want to look for hidden behavior. Like we did yesterday, we had to zoom in, and we could see that it was something that looked flat, wasn't. Okay, we could use a sign chart, but when we do inequalities, we're mostly going to be sticking to graphing. Okay. Algebraically, that's when we'll do the equations. Okay. Inequalities, we're gonna do graphing. All right, so let's take a look at this one. So we got 2x squared plus 6x minus 8 divided by 2x squared plus 5x minus 3 is less than 1. Okay, so let's type that in and see what happens. We actually might want to factor the denominator if we can, because remember, if you have vertical asymptotes, those can't be included in your answer. Those are undefined values. So that could control how you write your answer a little bit. So if we try to factor the bottom, we would have 2x squared plus 5x minus 3. Didn't we just do one like that? I thought we did. 2x squared, minus 5x minus 3. Well, it's almost going to factor the same way. We're just going to switch the signs. 2x minus 1, x plus 3. So that means I'm going to have vertical asymptotes at what numbers? Yep. 1/2 and -3. So what that means is when I write my answer to this problem, if I have to go from a number below -1/2 to a number below 1/2 to a number above 1/2, I'm going to have to break my interval. I can't go through 1/2. Right? Same thing with -3. If I need to go from below -3 to above -3, I'm going to have to break my interval at -3 and then continue on with the union symbol. All right. So that is helpful to know. All right, so we've got 2x squared plus 6x minus 8 divided by 2x squared plus 5x minus 3. So because we have two vertical asymptotes, how many pieces are we expecting the left-hand side to be in? Yeah, 3. Yeah, we're expecting 3 pieces on that left-hand side, and then we're going to have a horizontal line at 1, and we're going to be looking for where we are under the horizontal line. So make sure we typed in everything right. Okay, so let's start with zoom 6. Well, there's your 3 pieces, just like we expected. And we're looking for where we are under the number 1. Well, let's start with the middle section. Is the middle section ever under the number 1? No. So we don't have to worry about anything here. Now, let's see what happens on this left section. Okay, this is the section that goes right up to the vertical asymptote at -3. What I want to check is, I can see that it's under the red line, but the question is, does it ever go above it? Right? So what I'm going to do is type in an x value that's pretty far to the left and just take a look. Well, when I get all the way to -5,000, I'm at 0.9999. So I still haven't gone above -1. What that tells me is this blue section is probably always going to stay under the red line. So let's call it section 1. How far to the left can I go and I'll still be on section 1? Well, Ethan, what do you think? How far to the left can we go? To which way?
Negative.
Yeah, section 1 is going to go all the way to -infinity. And how far to the right can we go and make sure that we are still on section 1? Because we could agree section 1 is under the red line, so we don't want to leave section 1 yet. Yep.
You can go like, I don't know how to explain it, but like up to -3, but not really -3.
Up to, but not including -3. Yeah, exactly. So we use a parenthesis. So that section is under the red line. You don't have to worry about anything in section 2. Now, I'll call this one section 3. That one kind of looks like it's going above the red line at some point. If we check our table, look at what happens when x is 500. I'm at 1.001. So somewhere between like 2 and 500, I went above that red line. In fact, even somewhere between 2 and 25, I went above the red line. So I need to calculate that intercept. It's hard to see, but it is definitely there. It's at 5. So 5 is the highest that you can go in section 3 and still stay under the red line. And it did say under, it didn't say under or equal, so I need a parenthesis. What's the lowest that you can go in section 3? And make sure we're still under the red line. Think about the lowest number you can pick, and you'll stay on section 3. If you go past this number, you're going to end up in section 2. So don't go past that number. Yeah?
0.5.
0.5. Your vertical asymptote. You cannot go below 1/2. So those are the two intervals that are under the number 1. If you wanted to know where you are above 1, well, you could do that too. It'd be everywhere in interval 2. That's between the vertical asymptotes. Interval 1 we would exclude completely. And interval 3, it would be from numbers higher than 5. Because once you get over here, you end up above the red line. Okay. Any question on that one? And that's just another one that's pretty similar, solving graphically. But it's the same idea as this last one. All right, so any questions on solving rational equations algebraically with the LCD or inequalities graphically, like that? Okay. All right, so homework, I can change that just to okay, so it's 1 through 17 odd, and then seven other questions. 20 to 22, 24, 28, 31, and 32. Okay, so we will go over that tomorrow, and that finishes up everything on rational functions. So we talked about graphing them, solving them. Tomorrow we'll start 4.4, which is radical functions. And that'll be the last section that's on the test for this week.